Hi folks, Mr. Myers here. Sorry I can't be with you during class, but I wanted to take this opportunity and go back and review a little bit of what we did on Thursday and then get us up through molar mass. We're not going to get through using molar mass today, but we're going to wrap up mole ratio and then figure out how to calculate the molar mass. So as we can see, this is the slide that we had left off at. And if I'm going to switch over to the hover cam. All right. So an example of a mole ratio for this one, we had said for every 2 moles of magnesium, there are or is 1 mole of O2. Or for every 2 moles of Mg, there's 2 moles. And then we could relate oxygen. For every 1 mole of O2, there are 2 moles of MgO. Now these are fractions and conversion factors. Because they are conversion factors, that means that we can flip them and take the reciprocal depending on the calculation that we'll have. So we can relate it and say 2 moles of magnesium for every 1 mole of O2. And we could write for every 1 mole of O2, there are 2 moles of Mg. Okay? Either way, that's the relationship that we have going on. So as we flip the page in our notes, we had an example problem that we started off at in class. Okay? So calculate the number of moles of sodium oxide produced when 5 moles of solid oxygen gas. So I told you I'd always provide the equation for you. So we have sodium plus O2, Na2O. Some of you asked how we get Na2O. That's just the formula for sodium oxide. Sodium is in group 1 of the periodic table, which means it'll have a +1 charge. Oxygen is in group 6, which means it needs 2 more electrons to obtain its octet. So it's a -2 charge. When we go back to Chem 1 and cross multiply, we get Na2O. So this is the equation. And when balanced, we found we needed 4 sodium, 1 O2, and 2 sodium oxides. Now, we want to calculate moles of sodium oxide from 5 moles of solid sodium. So the mole ratio we're going to use from the equation, we know we have for every 2 moles of sodium oxide. Okay, this can also be rewritten or flipped over as 2 oxide for every 4 moles of sodium. So in step 3, we start with what we know. We know we have 5 moles of sodium, and we set up this T-chart, which in a lot of ways is just like multiplying fractions. So I'll write it that way as well in case you like fractions better. All right, so we go with the conversion factor. The idea is we have moles of sodium, and to put that, like I said, downstairs, we don't need it on display anymore. And the new unit that we want is mole oxide. Okay, notice I'm going to write this over here. You still see it? Yep. So 5 moles of sodium times, we've got a mole of sodium oxide. So we're going to take the conversion factor such that sodium oxide is on top. So 2, 4 on the bottom. Notice we're multiplying by fraction, 5 times 2 over 4. I fill it in over here. Now 5 times 2 is 10, divided by 4 is 2.5. So that means we have 2.5 moles of sodium oxide. This should make sense because we have twice as many moles of sodium as we do sodium oxide. Or flipped around, half as many moles of sodium oxide as we have sodium. So if we're starting at sodium and we go to a quantity that's half then half of 5 is 2.5. All right, let's look at the next example. It says calculate the number of moles of oxygen gas, that's O2, needed to burn 1.22 moles of ammonia. So we start with 1.22 moles of ammonia, and then we want to know moles of O2, and find the moles of nitrogen dioxide and water produced. Hold that thought. Sorry, in the middle of recording the video. There's an emergency. Okay. Sorry about that, folks. I'm just about everyone is sick at home. My wife hurt her hand over the out on Monday. I'm just helping out around the house. And that was my wife calling. So I apologize for going away there for a moment. But if we're back here, hopefully we went ahead and balanced the equation while I was gone. The O2, we have an odd number on the right side. But here, we're going to have to double some things. So the equation, if I have 4N, I need 4 of these. 4 times 3 is 12. So we need 6 waters. Oxygen, we have 8 plus 6 is 14, so 702. The reason I went ahead and made this a 4 is because originally I saw the 3 on the H and the 2 on the H and thought 6, least common multiple. Put a 2 here, put a 3 here. But doing so would give us an odd number of oxygens on the right while we have even on the left. So I have to double that again to get where we want to go. All right, so if we start with 1.22 moles of NH3, I know from the equation that there are 4 moles of NH3 that goes on bottom because we want to get rid of it, and 7 moles of O2 up on top. So put in our calculator. Oop, batteries are low. All right, so 1.22 times 7 divided by 4, 2.135 moles of O2. All right, now we want to find NO2. Notice how NH3 and NO2 are both 4 moles. That's a 1-to-1 ratio, so I'm not even going to calculate that. We'll just say 1.22 moles of NO2. And then we're going to go moles of NH3 to 6 moles of water for every 4 moles of NH3. 1.22 times 6 divided by 4, 1.83 moles of water. Okay, so there you go on that one. Okay, you can always pause this as we go, so keep up. Practice problem, the next one, it says refer back to the brownie recipe on page 1. It says if you have 2.5 teaspoons of vanilla, so 2.5 teaspoons of vanilla, how many tablespoons of salt will you use? So let's refer back to our recipe. Teaspoons, so vanilla and salt. So vanilla is 1 teaspoon, salt is a 1/4 teaspoon. All right, so vanilla, for every one teaspoon, there is 0.25 teaspoons of salt. And we have to convert it or make another conversion here because it asks for tablespoons of salt. I know the value because we cook a lot in our kitchen, but there are 3 teaspoons for every 1 tablespoon. You did not know this necessarily, but now you do. And so to calculate, we're going to do 2.5 teaspoons of vanilla times 0.25 teaspoons of salt divided by 3 on the denominator. So to multiply everything on top, divide by the product of what's in the denominator, and what we get is 0.2083 tablespoons of salt. And you can't even see what I was doing there, so I apologize. So there it is, 2.5 teaspoons of vanilla. For every 1 teaspoon of vanilla in the recipe, it requires 0.25 teaspoons of salt. There is 3 teaspoons for every 1 tablespoon. So we need this many tablespoons of salt. But that's going to be pretty hard to measure out. So this says most of the time we'll want times easily. And to do this, we just need to add one more step to the problem, which is molar mass. So if we go back up to our problem before, the idea is that, say we went from moles of ammonia, NH3, and we wanted to go to grams of water, we would convert it to moles of water first via the mole ratio, and then we can go to molar mass. Pretty neat and fancy. So we're going to bring up molar mass here. And right here. Okay. Pops up. All right, so molar mass, by definition, is the mass in grams of 1 mole of a substance. Okay. And 1 mole of a substance happens to represent an amount of particles. Mole is the SI unit for an amount of particles, specifically 6.02 times 10 to the 23 particles. And we'll find in our calculations this next couple weeks that particles can represent atoms, and it can represent, atoms, it can represent molecules. We might also see something called formula units. Formula units is the same concept as these, but relegated to ionic compounds or salts. Molecules are going to be covalent compounds because they're actually covalently bonded. Atoms would be elements, and then particles would just be in general. Okay, so mass in grams of 1 mole of a substance, 1 mole happens to have this many particles. And the way that we find molar mass, pretty straightforward. We go to the periodic table, PT, and we're going to add the average atomic masses, which are on the value with the decimal places in the bottom of each periodic table box, element box. So add the atomic mass for each element in a given formula, and that'll get us the molar mass. Okay, so as an example, it says find the molar mass of nickel hydroxide. So I'm going to go back to the hovercam here. Hovercam. All right, so find the molar mass of nickel 2 hydroxide. You will need to reference a periodic table, which I have not printed one off for you. So yeah, you can look up a periodic table with your Chromebook online, or if you have your phone. Let me show you something really fancy real quick. So this is my phone. I'm going to zoom out for a moment here. And under my utility, I have Merck PTE. Oops, wants me to sign in. You can tell I'm at school right now. All right, so this Merck PTE, if you go to your, was it the Google Play Store or the Apple App Store or something? I don't know. I've been an Android person for a long time. Just look up Merck PTE or Merck periodic table, and you'll come up with this one. And so this one I like a lot. It's very friendly, but it says if I go to nickel, number 28, the mass is 58.6934. The periodic table that you guys will use, which is this one, Nickel here is 58.69. So we've got 1 nickel. And then oxygen is 16, 2 of them. And hydrogen is 1.01, and there are 2 of them. So here's oxygen right there. Hydrogen out of the light. There we go, 1.01. So we've got 58.69 and 32 and 2.02. So we've got 1, 11, 7, 10, 12, 8, 9. So the molar mass is going to be 92.71 grams per mole. So remember, molar mass, we said, is the mass per mole of the substance. Okay. So in the periodic table with atomic masses, we've maybe previously learned about AMU, atomic mass unit. Atomic mass unit. So it'd be 92.71 AMUs. But when we put it in the context of a mole, we can say it's the mass. So the mass is 92.71 grams for every 1 mole of that substance. All right. I've been chatting here a while. How long? About 16 minutes. So we're going to call it good there. The assignment that you have this morning is going to be one side will have some mole ratio calculations. So write up the mole ratio or coefficient ratio and go from mole of one substance to another. And then I'll have some molar mass problems for you as well. All right. Have a good rest of the day and take care, guys.